So very different topic. Sorry, we're running a bit late. We now have the pleasure to have LCasali, first time at the festival, talking about plasma physics, origin integration.
Thank you. It's really nice actually to be here. So far, I've been enjoying being exposed to very different topics. So I'm gonna definitely switch gear from what we heard, although I have actually a couple of questions for you to talk about later. Okay, so I just wanted to introduce myself. So my name is LCasali. I graduate, so I'm Italian. I graduate in nuclear physics at the University of Rome. And then I actually moved to Germany, first to Freiburg, then in Munich, where I got my PhD at the Max Planck, working on acids upgrade, which is a mid-size tokamak in Munich. After that, I moved to General Atomics, where I work as postdoc and staff scientist, working on D3D tokamak. You might have heard also about that. This is now a carbon machine. So I switched from a tungsten machine to a carbon machine, which is kind of the inverse of what people are doing these days, as the tokamaks are actually switching to tungsten machine. So I always the joke, I went from tungsten to carbon. And then I accepted this faculty position at the University of Tennessee. And so I have been there now for a few years. Interesting fact about me, I graduated at the Bal Academy in Italy. So I was dancing professionally. And what I'm saying this for, because I know there are a lot of students here. And so what was actually surprising to me, at least at the time, is that a lot of the skills I learned back in the days used to be, they turn out quite useful for my career in science. Share is that my daughter has been seeing her first plasma at TCB back in December at age 2. So I'm very excited for hopefully have another physicist later on. Okay, so at the university I teach and I do research. In terms of the teaching, I created a new plasma physics course. Basic, but also kind of direct towards fusion. This is actually, so the course starts. So we start here. This is actually a prototype of a bumpy torus that is outside our building. The bumpy torus was a prototype funded by NASA. So NASA during the 1970 was actually investing a lot of fundings into these prototypes. So there have been several that have been built, and then they were abandoned actually because of turbulent problems fundamentally, and then tokamak became the most important configuration that was used. Then I'm also teaching. I created a radiation shielding course. This includes both fission and fusion, fusion neutronics, introduction to blankets, and Monte Carlo neutron transport using both MCNP and OpenMC. So in terms of my research group instead, so I have a very nice research group where we do a lot of different things. We work mostly on trying to solve the problem I'll talk to you today, which is the issue of core edge integration, specifically in tokamaks. So we work on both experiments, so design experiments, run experiments in the control room, and then we also do simulations. Perhaps the biggest focus is on edge and boundary physics, so on the Werther geometry, recycling, and advanced the Werther configurations, and then we try to couple the edge physics to the different regions that I'll talk a little bit more in a second. So the pedestal region and the plasma core. And then lately, together with the development of my class in shielding, I actually started to work quite a lot on neutronics and introducing information from the plasma physics into the neutronics as well. I will probably have no time to talk about that, but if you're interested, I'm happy to talk to you later in this afternoon on that. Okay, so biggest problem we have in tokamaks. So first of all, the edge region encompasses the boundary layers between the core, which is hot, and the edge and the material walls. The fundamental challenge becomes from the fact that we have really different conditions on the core. We need to have hot temperatures in order to actually make fusion in the center. And then we actually need to have quite cold conditions, the diverter materials to not melt our devices. These heat fluxes that are impinging on this region, which is called diverter, can be higher than the one that are in a rock nozzle. And so you understand that we have huge gradients into our plasma, and it's really difficult to integrate these different regions. And so this is an example of a melted tile after operation. These fundamental challenge also arises from the fact it actually gets worse as we try to build reactors, because practically we estimate that if we do not mitigate these fluxes that arrive in here at the diverter, these target loads are going to be above 300 megawatt per square meter. However, we have two very important limits that we need to be below, and these are the target heat fluxes. So a Q that needs to be below 10 eV, better if it's below 5, and also the target temperature below 5 eV. This means that we need to increase the power dissipation up to 95% in future devices. So that's where the challenge is coming from. So now to give you the idea, so on one side we have the core of the plasma. We want the core to be, of course, high performance because we want to make fusion. It's hot and is fully ionized. Then we have the diverter region, so where we have edge physics. In this case, we want high density, is very cold, is not fully ionized, and involves practically the interaction with all the PMI physics, so the plasma wall interaction and problems with erosion and neutral particles. So these two different worlds now are meeting in a very tiny region that is called the pedestal. Interesting fact is that if you like, the density at the separatrix, where the separatrix is, this last closed surface, is the one that is constraining somehow both the core and the diverter. However, most of the information when we try to project to power plants are on any pad, on the pedestal density, which is up here. But really, the constraints come from the separatric density, where, however, we have not really good measurements. And so you understanding what is the problem that we are facing. This NESEP is set by diverter detachment and by parallel transport. So in the pedestal region, and I know there have been few talks about this through the week, so you have already heard about this H-mode pedestal, so I'll introduce that very quickly. So this is the standard way where we operate a tokamak. We operate in a donut shape, is a D shape. This H confinement has been discovered at ASDEX back in the 80s. So practically was discovered that the plasma could naturally transit to a improve confinement naturally due to the fact that there is suppression of the turbulence. So you can see here from the fluctuation level and going from what we call the low confinement state and L mode to H mode. What comes, however, with this H mode is the appearance of these ELMs, which are instabilities at the edge of the plasma. They are transient, and they are expelling heat and particles practically through the separatrix and to the materials, which is something we cannot tolerate in fusion reactors. The issue is that our normal way to operate the tokamak, it is optimized for good confinement, however, is not optimized for power handling. So the main question we have been trying to answer for quite some time at this point has been, how can we reduce these diverter loads to match the technological limits I told you before? Fundamentally, we have two tools. One is radiative cooling. So we inject impurities into the plasma in order to practically radiate and lower the power loads. However, this radiation needs to be compatible with the dilution. We don't want to have radiation in the very core because that's where we need to make fusion. So we don't want to dilute. Also can create MHD instabilities. And so we need to be careful about that. And so we have to avoid that there is too much impurity that are going into the core and eventually accumulate. And so I can't practically make fusion anymore. The other way that we have is what we call diverter detachment. It is a cold and dissipative state where the diverter is finding itself now. Usually the temperature is below 2 eV, and we have a reduced heat and particle fluxes. And this is a nice sketch which shows practically how the parallel heat flux will be reduced as we go from an attached state to a fully detached case. Okay, great. So now I know I can radiate, but the question is, how do I choose which is the right impurity if I want to radiate in a specific region of the plasma? The answer comes from the atomic data. I'm showing here the LZ, which is the efficiency, if you like, of an impurity as a function of the temperature. And so I can see from this plot that nitrogen and carbon radiates at the diverter, then they're fully ionized. Argon and krypton, they still radiate significantly at higher temperatures. And so carbon and nitrogen are good for edge diverter radiation, whereas argon and krypton are good candidates for main chamber radiation, so for mantle radiation. One important thing that we need to consider when we talk about purity radiation is the existence of non-coronal effects. So practically, if we neglect the transport, there is a balance between ionization and recombination. This is as in the solar corona fundamentally, which is why it's called the coronal equilibrium. In this case, LZ, which is the efficiency of the impurity I showed you earlier, is only a function of TE. So easy. I calculate P rad as electron density, purity density, and LZ. However, at the plasma edge, where I have these steep gradients and these ELMs that I was showing you before, the radial transport cannot be neglected. And we are in a state that we call the non-coronal equilibrium. And in this case, LZ is not only a function of the temperature, but is a function of the temperature and of NT tau, where tau is the residence time for an impurity. So we have done some work, and I'll try to talk about that later, where we are using our self-consistent model of plasma transport and radiation. This is the Astra and Strahl code, so they are coupled. The coupling allows that at each time step, as we evolve the temperature and the density in the plasma, also the radiation and the zeta effective get information from the impurity transport, because most likely if you are radiating, your temperature will go down and your radiation will change. And so this needs to be reflected into the background transport. And so from these calculations, we saw that, for instance, in the case of nitrogen, if we consider now the N tau, so with the different residence time, there can be really a large difference between our approximation in corona. So fundamentally, doing a coronal approximation is not the right thing to do at the plasma edge with low Z impurities. We were able to show that these non-coronal effects are important for low Z, but not for high Z, and this is because of the high ionization and the recombination rate. However, this business of the non-coronal is really important because one of the main questions we are trying to answer to actually design a reactor is what is the impurity concentration that we need to have to detach the diverter. And so here we are again at the plasma edge with the low Z impurity. So a difference of this kind is, of course, very important. So we need to be able to have a non-coronal equilibrium. Showing using this framework that I was just telling you about, we were, for instance, able to predict correctly a radiation collapse induced by tungsten. We did this in ASDEX, and whenever we were reducing the Helm frequency. So, for instance, these are time trace from tungsten. If we were at high Helm frequency, we could see a kind of like nice time traces of the density as we go lower and lower in the Helm frequency. As you can see, we could start to see the accumulation of tungsten into the discharge. However, we did not see the behavior in nitrogen, and that because fundamentally the different behavior between impurity is governed by neoclassical transport theory, which tells us that practically scales with the Z. So for tungsten, which is 73, is very important, but is not important for low Z impurity, such as nitrogen. And so we were able to see exactly this radiation collapse that was happening in the experiments at the Helm frequency we were trying to model. So this was showing then the importance of having an edge transport. In this case was a high Helm frequency, but it could be anything, a kind of transport that will remove the impurity from inside the pedestal and put them back out. Okay, so now going back to the detachment physics, which is my other tool to try to reduce the loads, I would like to know how this process for power dissipation really works. So practically, if we are in the open field line of the tokamak, we can draw this sketch where we have the impurity radiation zone. So this is a place where now nitrogen and carbon radiates very strongly, as you saw from the LZ function I was showing before. So now I'm able to drop the temperature below 10 eV, around 5 eV, where I find the ionization and the recombination zone. At that point, there are other processes like charge exchange and so on that are and neutral processes that are also now able to lower the temperature to 1 eV, where the recombination zone is found. There is a nice figure that sometimes I like to show. This is an old one because it kind of gives really the idea of how complex is this physics. There are a lot of things are happening, ionization and dissociation of the recycling atoms and molecules, a recombination region. And this is, by the way, because we have this complex atomic physics, this is the reason why we cannot have scaling approach in the edge part of the plasma compared to, for instance, what we do in the core of the plasma. This is exactly the reason, because of this complex atomic physics. So what can we do about it? Well, we can use a couple fluid kinetic codes, usually 2D and 3D. And I'm just here mentioning some, like the salt PS heater or U-edge, sol edge, edge 2D array. We have a series of codes. These are practically a coupling of a 2D. I'm showing this for salt PS heater, but it is the same for everybody. Is the coupling of 2D multi-fluid plasma, so we're solving Braginski, and 3D Monte Carlo kinetic neutral, so in this case, Irene. In practice, we have our multi-fluid plasma code. This provides the plasma background, so NE, TE, TI, to Irene, that now evolves the sources and the sinks that are due to moleculars and to neutral, and provide these terms of the sources and the momentum, and gives this back now to the fluid code to move at the next step. Okay, so this is the tool that we have that we can use. Let me go back to the experiments. So we want to do detachment because that helps my diverter loads. However, I have a problem. He has been shown in many machines. I'm showing an example for jet, but this has been shown everywhere at this point, that if I obtain detachment by increasing the gas path, so increasing just the density, my confinement decrease. And so I don't want that. It's a problem. There are other examples, more recent example, again, from different machines. In this case, I'm showing here something from my own research, that if we combine what we call diverter closure, so we try to close the diverter so we can help power dissipation in the diverter, and we use impurity, then we can achieve improved courage compatibility. So this is a case where we are injecting nitrogen into the discharge. We see a big rise in the neutral pressure in the diverter, which is a sign that we are getting close to detachment, and the WMHD, so the store energy of the plasma, stays constant here through this phase also of the very high peak of nitrogen. So this idea of the detachment onset has been, that is influenced by this diverter buffering, has been extensively studied. There are cases from CMO, JD60, ASDEX, JET, and so on. So this is something that has been seen through the years. And one of the things that we were trying to answer back a few years ago, but what it is actually diverter closure? So the terms kind of refers to the degree in which the recycling neutrals from the target can escape the diverter. So I'm showing this, the Monte Carlo trajectory of neutrals. These are calculated from Marine, so from the Monte Carlo. And this is the closed and the open diverter of D3D. You can see this clearly, that in the closed diverter, the neutrals accumulated the target, whereas in the open diverter, you can see here, they practically go everywhere. So there is no accumulation. Okay. So we defined kind of a metric for diverter leakage, so we call it the DLP, and practically is practically showing just that we can count this as the number of the neutrals that are escaping the diverter over the number of neutrals that are born in the diverter. So I have recycling and I have recombination. Okay. So if I now go and plot for my experiments, these metric for diverter leakage, I'll find out that the closed diverter is much more efficient in trapping this neutral. This parameter is much higher in the open diverter compared to the closed diverter. And then if we are here and we plot the practically ionization to the plot, you can see here that in the open diverter, there is a leakage of neutrals on both sides. But here, where the diverter is actually closed, this leakage is blocked. So now I'm keeping my neutrals in the diverter, and I can distribute this more. Okay. So then we wanted to try to understand better this behavior. And so we went and plotted the radiation in the open diverter and in the closed diverter. Now the PNet, which I'm showing here in black, we can compare to the experiments. And so we did. The nice part of doing the simulation is that now we can actually break the contribution of the radiation into their components. And so we could practically break these in line radiation, neutral radiation, and ion neutral losses. So we could see what was the main contribution that was changing as I would change the configuration. So we saw that there were higher losses in the closed diverter, with almost 40% higher than in the open diverter. And this is contribution, as for instance, done in SOL-PS, is the sum of these terms, so LAN radiation, neutral radiation, and ion neutral losses. Carbon, because we have a carbon machine, this is a carbon machine, is the dominant radiation loss, contribute with 85% in the open diverter, but only 50% in the closed diverter. In fact, the neutral radiation now and the ion neutral losses have a higher contribution in the closed diverter compared to the open, exactly because of this closure mechanism I was showing you. Okay, so now we wanted to understand something that we saw experimentally. So experimentally, we saw that the closed diverter was detaching at a lower density than the open diverter, which is a great news for core edge integration. That's what we wanted. But why? So we have performed more analysis with the use of SOL-PS, always applied to the experiments. And so in this case, practically, we were able to show that in the closed diverter, and actually it's pretty intuitive, in the closed diverter, the neutrals cannot escape, okay? So I'm trapping them. So there is no particle flow. And so the heat must be conducted by conduction fundamentally, which has a strong temperature dependence, right, to the 5-2. Whereas in the open diverter, a lot of the flux, in fact, is 2/3, is carried by convection. But in the closed diverter, I almost have no convection. In fact, it's just a layer in front of the target. Then we took the 2-point model, which is practically a simplified model to characterize the upstream, to connect the upstream with the diverter conditions, as shown here. And we practically insert the numbers we were getting out of the simulation in the model for both of the geometry. And we found that the values was very consistent with the percentage that we found for the upstream density at the detachment onset. So we were able to kind of give an explanation for why this diverter was detaching a lower upstream density.
Just a quick question.
Yes.
You somehow escape from getting into a flux limited regime? You know, the question of the form of the thermal conduction, right? This is a nagging issue.
This is for a longer conversation.
Okay,
So
okay.
yeah, for later. Yes, yes. Okay, so then we did this first impurity CD in what is a slot diverter. It's called SAS. I'm showing this right here. So this was installed at D3D. So this was the figure I was showing you earlier. What was special about these experiments, because as I told you, these closed and slot diverter specifically was already actually looked at earlier at Alcador Simon, was that we had at that point an unprecedented number of diagnostics to look into the slot, which we never had before. So now we have a slot and we have all the measurements possible you can think to look into that. And so these experiments led to the first simultaneous observation of detachment on this entire diagnostic suite. In this case, for instance, I always like to show this because it really shows a nice correlation with the diverter Thomson scattering that measured the temperature. But this is a spectrometer, is infrared spectrometer that is revealing now the appearance of the Paschen lines that only appears when the temperature is below 2 eV. So we know for a fact the temperature is below 2 eV. The diverter Thomson has measures temperature below 0.5. And then we have a lot of other different diagnostics independently showing the same behavior. So we could also see that this detachment in front was not just localized, but was a larger phenomenon that was spread through all the slot. Then we did experiments where we were trying to keep the radiation fraction constant, but we use neon instead of nitrogen. And so one thing that we could see, these are again the experiments. Practically, we didn't see much changes happening with nitrogen, but we could see a steepening of the gradient happening with the neon. So we wanted to understand what was the physics that was governing the impurity leakage mechanism. And so we use saltpeter heater, we use impurity distribution as implemented in saltpeter heater. And so we applied this and found that the dominant forces are the thermal and the frictions with the main ions. Okay. Then what I can do, I can get the momentum balance and I derive the parallel velocity for an impurity. This term practically can be described as the main ion parallel velocity and the term that depends on the gradient of the temperature. So if I go and plot the parallel velocity, in this case for nitrogen on top and neon on the bottom, the large difference between the curve with the magenta one is, the thermal force. So this difference is due to a thermal force. What does that mean? It means that now I have a force that is extracting the impurity out of the diverter. This can lead to what we call the flow reversal. So a flow away from the diverter, which can happen in a flux tube, for instance, when the ionization exceeds the ion loss. This has been theoretically predicted back in the days and also experimentally measured. So we found the same thing here in this work. So we saw flow reversal in both the main ions and also on the impurities. So now, when we see an impurity that is reversed, there are two options. So either the impurity is reversed because the main ions are already reversed, which was partially the case here, but also if I have a very strong thermal force, which is also the case here. And so if I have a thermal force, which in this case was created by the strong ionization that I have in the diverter, now the impurities are leaving the diverter and they're going upstream. And this might become a problem. So we were able to kind of put the puzzle together. So in the case of the neon, so neon is now leaving the diverter. And because of this mechanism of impurity leakage I just described to you, and now is building in the pedestal, so we are inside the separatrix. There is an increase in the diamagnetic frequency, which is practically helping the stabilization of the pedestal. So this is the peeling ballooning stability. And we can see with time, so as we increase the amount of the impurity, we can get a more stable pedestal. So we get a more stable pedestal. We have a radiative mantle, so neon is also radiating through the separatrix, and this is lowering the ELM frequency, so the frequency of this instability. And so there is a cycle that kind of starts and keep on looping. Now, if we decrease this ELM frequency, it also means that we have less possibility to flush out this impurity outside. And this leads to an important, raises actually an important question, because for reactors, we want to actually work in a regime where we have small ELMs, so as in this case we were getting, or non-ELMs at all, even better, but at high confinement and in detached state. Okay, so there is a list of scenarios that people are exploring in the community. There are like, these are called QCE, EDA, I mode, QH mode, and so on. The last two are the two I've been personally looking at. And so these are the X-point radiator and the negative triangularity. And if you like, these are two different approaches. I called it, so the negative triangularity is without a barrier, and I'll introduce this in a second. And then with the X radiator, we are actually controlling the front. So there are two different ways where we are trying to control better, if you like, the radiation. What is common to all of these scenarios is that we are practically trying to get an edge transport by turbulence or coherent mode as a mechanism to get a stability in the peeling ballooning space and the suppression of type 1 ELMs. So one of the first scenarios I mentioned is a deep point radiator observed practically in most of the machines. At this stage is a cold and dense region inside the plasma. This is a figure from Aztec subgrade that is showing, for instance, here how the ELM becomes ELM-free when this XPR is reached. Why this is of interest? Well, because this kind of regime seems to be obtaining a full detachment, a high radiative fraction, which is also what we want, an ELM suppressed regime, also compatible with good confinement. The location of this front is happening, is influenced by impurity seeding or the level of how much heat we put in the plasma. And so this means that we need to control, we need to be able to control these scenarios very well. In fact, this is kind of a development of the, probably of the MARF scenario that have been seen for decades before, but now is possible to control this better. We actually are pretty happy to say that I was able to perform this experiment 3 weeks ago at D3D. So these are super preliminary experiments. But I just wanted to show you. So these are experiments in XPR in high beta hybrid. So a very high confinement and performance with argoside at 50 megawatt. So in this case, we are able to get this region ELM-free with very low temperatures as shown by the probes and by the Taborov-Thomson that is showing temperature at this point below 1 EB. So a lot of work here to do. I need to analyze the data, but because here there was not really the D3D machine I wanted to show, we actually did these experiments and eventually we'll be able to tell more. The other, I don't know how much time I have, please stop me anytime. Okay. Oh, okay. All right. So, okay, let me tell you this quickly. So this is what I think is actually a very exciting, probably the next frontier in Tokamak physics, at least in my opinion, and also Pat's opinion, I think. So courage integration without barriers, negative triangularity. Okay, so we have performed a month campaign in D3D, studying this regime, where now instead of the classic D shape, let me switch here, we are actually operating in a reverse D shape. So this is the negative triangularity experimental case that we were able to build. Why we are interested in negative triangularity? Okay, so I told you that in positive triangularity is great for confinement, however, is bad for power loads. We don't want to have ELMs. There is a small level area and we need to stay above the LH threshold, so that threshold for which I can be in high confinement, where the turbulence is reduced. In negative triangularity, it has been shown at TCV and at D3D that we can actually get confinement of the level of an H mode, but we don't have ELMs intrinsically. Theoretically, in a reactor, we could have a larger diverter, and there is no power threshold. The fact that there is no power threshold, it means that we are in principle able to radiate more in this region of the plasma that we called mantle. So if you remember at the very first, I told you we need to maximize the radiation up to 95%. In order to do that, we need to radiate in the diverter, so outside here, right, the project, and we also need to radiate here in this orange region, okay, but not in the core. We don't want to radiate in the core because we still need to make fusion. Okay, so however, in positive triangularity, I have a limit of how much radiation can I actually do in here, and the reason comes from the necessity to stay in H mode from above that pedestal that I told you about. This is driving the major power exhaust issue we have in positive triangularity. And everything is, for instance, in this paper here. However, the point is, if now I can reduce, I can remove actually this problem. So in negative triangularity, I don't have this H mode, I don't have this pedestal, so I don't have to be in this condition where my power of the scrape of layer needs to be above the transition because there is no transition. Then in principle, I could radiate more. So that's what we wanted to try and verify in negative triangularity. So again, I go to my plot of the LZ, I look which impurity I want to use, and I choose the impurity, and then I go and do my experiment. I do the experiment. So these are experimenting very strong negative triangularity, minus 0.5. These are intrinsically free, so we never see these instabilities. And we can see that with all the different radiators, we can actually see an increase in beta N, so the normalized pressure, some general of confinement, as the radiation increases. And this can be obtained, except for neon, because I told you neon accumulates, as I showed you before. And at the same time, we can actually achieve a simultaneous reduction of the heat fluxes with all radiators in the diverter. This also obtained with a good agreement with the SOL-PS simulations. We have done a lot of experiments, okay? Just tell me when I need to stop. I guess maybe a couple of minutes to finish here. So we have done a lot of experiments. Yeah, I know. That's what I say. Okay, I got 2 more minutes to finish this. Okay, so we did the first characterization of the operational space at a high radiation fraction and high greenfield fraction, and we try all these parent combination of parameters. This was one of the cases where we really pushed the operational limits. So we had experiments with krypton, where we could achieve a really high radiation fraction, which this was accompanied then by an increase in the density till we get the, okay, this is very experimentally, but so practically we get the ECH cutoff, and so at that point we lost the control. But in general, so these show a really good path to actually optimize these discharges. Let me go towards, this is relevant actually, because what was great to see is that we had with krypton seeding and with every other impurities that we worked, we could see an increase in plasma performance with increased radiation fraction. We could see a large increase in TI over TE, the density, large increase in rotation due to Crosby shear that reduced turbulence. Measurements from the BS here were showing, so going from black then to red and to blue. So here we had a reduction in turbulence when krypton was in the plasma. And we have found this behavior in all data set and also supported by simulations and analysis work with T gyro and TGLF. This is also a similar physics to what was found back in the year 2000 with RI mode, so in L mode. So it was actually showing that the mechanism for confinement improvement in negative triangularity is similar to the positive, however, is already building on a different and reduced turbulence in the core that we find in negative triangularity. We could see very clearly a reduction in the ion heat flux by a factor of 2, and the momentum diffusion decreases. We could also see the increase of the ITG region compared to the TM. Okay, I will try to stop now. I had a lot of other slides, but as a summary for the NT, so we have shown, we have demonstrated experimentally and also supported by all analysis and simulation that we have obtained high performance and high radiated plasma with reactor relevant CD gases in negative triangularity. And from the kind of edge physics analysis, which I wasn't able to show you, but I can show you separately if you are interested. We also see that indeed we can obtain this heat flux reduction simultaneously with an improving confinement with a lot of interesting mechanism of particle drifts and the divergent geometry. So to close the loop, so this was our experiments with a negative triangularity, and these are the Irene Monte Carlo trajectories, as I showed you earlier for the divergent closure. And so you can see here we had a lot of open space in this case. So practically, the conclusion also of this work was that we needed the closed diverter also in this configuration to enable to practically trap more neutrals and impurity. And so this brings the connections between the diverter and the confinement region, so they correct. Okay, all right, I take this.